Hello my dear students, welcome back to Fluid Mechanics lecture series. I am your SumamMiss. My channel name is also SumamMiss. You can watch all my videos on my channel. Today we are continuing the discussion of open channel flow, and the topic for today's discussion is gradually varied flow. Flow in an open channel may be either uniform or non-uniform flow. In uniform flow, the depth of flow remains constant throughout the length of the channel. So this type of flow is possible in prismatic channel of sufficient length. We have learned previously that the uniform flow is characterized by parallelism of channel bottom, liquid surface and the energy line. Non-uniform flow or varied flow is steady non-uniform flow in which flow depth changes in the flow direction. Now let us discuss about the cause of gradually varied flow. As we have discussed, gradually varied flow is steady non-uniform flow where the flow characteristics changes in the direction of the flow. Whether this variation is in small rate or in large scale, it varies in the direction of the flow. Gradually varied flow may be caused as a result of the change in size and shape of the cross section of the channel, change in bed slope, obstruction in the direction of the flow, that means due to the construction of the weir or dam in the flow direction, and change of roughness or change of frictional force at boundaries. So these are the main reasons which causes gradually varied flow. Now let us discuss the importance of analyzing this gradually varied flow. So within this condition we can say that pressure distribution in any vertical is hydrostatic, because for a small sloped prismatic channel without the turbulence, the streamlines are straight and parallel. So in that case, the pressure distribution in any vertical is hydrostatic. In the design of open channel, it may be necessary to calculate the flow pattern for getting the surface profiles and the length over which backwater effects due to the construction of hydraulic structures like dam, reservoirs, weirs, etc. As we had discussed earlier, the analysis of open channel flow is very complex due to the effect of natural factors, the variation of surface roughness, change in cross section in the direction of the flow. In order to simplify the derivation of the dynamic equation of gradually varied flow, we have to follow certain assumptions. The first one is bottom slope of the channel is very small. Then the channel is prismatic. Then energy correction factor is unity. The next one is roughness of the channel is constant and it is independent of depth of flow. So within these conditions we can apply uniform flow discharge equations for the computation of energy slope. That means we can use Manning's equation or Chase's equation for the computation of the slope of the energy gradient. Now let us discuss the derivation of dynamic equation of gradually varied flow, for which we can consider a longitudinal section of the channel. So consider the section as shown in this figure, which is at a distance of z with respect to the datum, and y is the flow depth. So dy by dx, which indicate the slope of the water surface. Sf is the slope of the energy line and S0 is the bed slope. So total energy head at this section is indicated by H, and it is equal to Z plus Y plus V square by 2G. Since it is steady non-uniform flow, continuity equation is valid. So we can replace V in terms of Q by A. So if we are replacing V in terms of Q by A and rewriting this expression, then we can write H equal to Q square by 2GA square plus Y plus Z. So SF equal to dH by dx. So in order to find out the slope of this energy line, we have to differentiate this expression with respect to x. So dH by dx equal to dy by dx of q square by 2ga square plus dy by dx plus dz by dx equal to minus q square by ga cube into dA by dx plus dy by dx plus dz by dx. So what is this dA by dx? That is variation of the cross section along the length of the channel. So from total derivative, we can express dA by dx equal to dA by dy into dy by dx. What is this dA by dy? It is the top width t. So that means dA by dx equal to t into dy by dx. So here you can see that energy line is sloping downward, or energy is decreased in the direction of the flow. So dH by dx can be written as minus SF, and dz by dx can be written as minus S naught, because bed slope is also decreasing in the direction of the flow. After substituting this expression will be minus SF equal to minus q square by ga cube into dA by dx plus dy by dx minus S naught. dA by dx is now replaced by t into dy by dx. So this expression turn into minus SF equal to minus q square by ga cube into t into dy by dx plus dy by dx minus S naught. So if you are expressing this equation for dy by dx, that is the slope of this water surface, that is equal to S naught minus SF divided by 1 minus q square t by ga cube. So this equation represents the dynamic equation of gradually varied flow. Now let us discuss about a different form of the dynamic equation of gradually varied flow. This equation is modified by keeping S naught outside as S naught into 1 minus SF by S naught divided by 1 minus q square t by ga cube. Now we are going to express this equation in terms of conveyance and section factor. So for which we have to use Manning's or Chassis discharge equation for uniform flow. According to Manning's formula, Q equal to 1 by n A r raised to 2/3 into SF raised to half. So here n is Manning's roughness, A is the cross section of the channel, r is the hydraulic radius, and SF is the slope of this energy line. So among which 1 by n A r raised to 2/3 is called conveyance, or it is indicated by K. So this expression equal to Q equal to K into SF raised to half. So the same expression we can write as Q equal to Kn into S naught raised to half. So Kn represents the conveyance in uniform flow condition, and S naught is the bed slope. If we are following Chassis formula, then Q equal to AC into root of R into SF. So here conveyance equal to A into C into root of R, or this equation can be written as K into root of SF. So the same expression can be written in uniform flow condition as Q equal to Kn into root of S naught, because in uniform flow condition SF equal to S naught. So if you are dividing SF by S naught, then expressing that in terms of conveyance, then SF by S naught equal to Kn by K the whole square. Another interesting thing is, in the denominator, Q square T by Ga cube is Q square by G divided by AQ by T. What is Q square by G? Q square by G represents the square of section factor in critical flow condition. Similarly, AQ by T is the square of the section factor in the flow condition. So Q square by G divided by AQ by T, that is equal to ZC square divided by Z square. So if you are replacing SF by S naught as Kn by K the whole square, and Q square T by Ga cube as ZC by Z the whole square, then this dynamic equation dy by dx equal to S naught into 1 minus Kn by K the whole square divided by 1 minus Zc by Z the whole square. So remember, this dynamic equation of gradually varied flow is valid for all channels irrespective of the shape. Now let us apply this equation for a wide rectangular channel. So what is the specialty of wide rectangular channel? A channel in which the width of the channel is many times higher than the flow depth, or it is more than 10 times the flow depth, then it is known as wide rectangular channel. So for a wide rectangular channel, hydraulic radius R equal to A divided by P. Since it is a rectangular channel, A equal to By, and wetted perimeter P, that is equal to B plus 2y. Since y is very small, we can neglect this. So b can be cancelled. So r is approximated to y. So the dynamic equation, that is equal to S naught minus SF by 1 minus q square t by Ga cube, or it is equal to S naught into 1 minus S of by S naught divided by 1 minus Q square T by Ga cube. Now we are going to modify this equation for a wide rectangular channel. You are starting from Manning's formula. So it is 1 by n a y raised to 2/3 s of raised to half. Instead of r, I replace y. Now substitute a in terms of by. So q equal to 1 by n by into y raised to 2/3 into s of raised to half. In uniform flow conditions, q can be expressed as 1 by n b into yn, because yn is the normal depth, into yn raised to 2/3 into s naught raised to half. So from which we can write s of by s naught as yn divided by y raised to 10 by 3. If we are using Chassis formula, then q equal to ac into root of r into sf. R is replaced by y and a is replaced by by. So in uniform flow condition, this equation is q equal to c into b into yn into root of yn by s naught. So if you are using Chassis formula, then the expression for s of by s naught equal to yn by y the whole cube. Next is replacement of q square t by ga cube. So it is a rectangular channel. So we can express q in terms of q into b, where small q is the discharge per unit width and b is the width of the channel. So q square t by ga cube can be replaced by q square b square into t equal to b, because for a rectangular channel top width and bottom width are equal, then g into b cube into y cube. So we can simplify this as q square by gy cube. Now what is q square by g? So we have learned previously that q square by g, that is equal to yc cube, or q square t by ga cube, that is equal to yc cube divided by y cube. So the dynamic equation for a wide rectangular channel turn into dy by dx equal to s naught into 1 minus yn by y raised to 10 by 3 divided by 1 minus yc by y the whole cube. If you are following Manning's formula, dy by dx equal to s naught into 1 minus yn by y raised to 3 divided by 1 minus yc by y raised to 3 if you are using Chassis formula. So slight variation you can observe, because here the exponent is 3.1, whereas here this exponent is 3. Now the session comes to an end. We started with the definition of gradually varied flow, and we have discussed the various situations where the flow becomes non-uniform, and also discuss about the various assumptions we can utilize for the simplification of the derivation of dynamic equation of gradually varied flow, derived different forms of the equation in terms of conveyance and section factor. We simplified this expression for a wide rectangular channel. So for the time being it is enough. Thank you.